Hello together. Welcome to our webinar Skiving, the high-speed turning for electromobility. But first things first, I want to explain something about the chat. You have the possibility to send us your questions, but please be aware everyone in the chat can see who tells the question. And if you send us your questions anonymous, you can use the question button at the bottom of the screen, and we also get these questions. We try to give you an answer live in this webinar, but for questions what we cannot answer now, we will collect all questions and give you an answer later. And now let's start with the webinar. What's the point? What we want to talk about? First, basic information. What is skiving? What is twist? The original reason for design and development of the skiving process. How skiving works. Some examples: skiving in hard and soft machining, and the achievable qualities. After it, some application examples, further reasons for skiving process, maybe cycle time, cost per piece, and so on, and some practical examples. After it, we have a short look on the machines, what we use for the skiving process, and at last we will have a conclusion. And now, here with me in the studio, my name is Andreas Druffe, I'm the product manager for shaft turning machines, and here with me in the studio is Daniel Nille, our expert for technologies and also for the skiving process. And now, Daniel.
Hello, my name is Daniel Nille. I've been working in technology development at EMAG since 15 years and was also involved in the development of the skiving process. What was the reason why we have developed the skiving process? If you have, for example, a sealing diameter, there is often the requirement that it has to be scroll or lead free. And normally the only possibility was to produce it with the grinding process. And so we decided we have to develop a new technology that we can produce scroll free or twist free surface with defined cutting edge. Yes, what is if we have a look at conventional turning, I can explain you what is scroll or lead. We have here the workpiece which is rotating, and the blue one is the cutting insert, and the cutting insert is moving in Z direction, and so you get something like a very small thread on the surface of the workpiece, and this thread has the problem that it transports the oil underneath the sealing, and because of this, the surface which are in contact with the sealing diameter they have to be lead free. And with the skiving process, it's possible to produce a surface which has not this transport effect for the oil. So here we see on the left side, we see our skiving insert here. It's a bit different than a standard cutting insert. It is a very long insert. It is limited to a length of 50 millimeters. And the tool is moving. It has a tangential moving. It's moving in the y-axis, and so the first point of contact is here on this edge, and the point of contact is moving along the cutting insert. And this this is good because we don't have such a thermal influence on every point of the cutting insert, because it has only a very short contact to the workpiece. Normally, because the length of the cutting insert is limited to 50 millimeters and the insert is mounted on 45 degrees, the maximum cutting length is something around 35 millimeters. If we have to produce a longer diameter, then we can use an additional set feed, which showed here. We can move during the insert moves in the y-axis. We can also move in the z-axis, and so we can produce longer diameters, but then it's not lead-free. Next page, we have an example for soft machining. Skiving is possible to use in soft machining and hard machining. And this here is an example for soft machining with no additional set movement. Here you can see that the insert is moving in the y direction, and then you can see the moving contact point at the cutting insert. The next page is we show you a video with additional set movement. It's needed if you have to produce a longer diameter. Yeah, but this one is not lead-free then.
Sorry, I have to interrupt.
Okay.
We have first question. How do you program or correct scroll-free turning?
Okay, program is very easy. We have developed a special cycle for skiving process that makes it possible for everybody to program this. You only have to give the cycle some parameters like diameter, cutting speed, feed rate, and so on. And we calculate everything in the background, and the machine makes the movement for itself. Correction is also possible. This is nearly the same than with the conventional turning process. You can do a correction on the length of the tool or a cone direction, and you can use it in the EMAG correction as a EMAG feature correction live during the process.
Okay, thank you.
So here we see an example for the hard skiving. We see the whole process in the machine. At first, our turret brings the part for itself into the machine. Then we have a measurement in Z direction that we exactly know where is the part. At the beginning, we do a pre-turning with a standard conventional turning process. I will tell you later why we need this. And after that, you can see the skiving process. And what you can see here, the chips are very hot. That's good because then the complete heat goes away from the process with the chips and don't goes into the part. Now the second turret brings the part out of the machine.
Nach oben. Vorhin.
Okay, sorry. So, what are achievable qualities with skiving process? We have here two different sections. The left one is for RZ 1 to 4, and the right one is for RZ better than 1. What's the reason? Normally, if you grind the skiving insert, it's the surface quality of the insert is better than RZ1. And we copy completely the surface from the cutting insert to the workpiece. The feed rate from skiving has nearly no influence on the surface quality. We only copy the surface from the insert on the workpiece. And it means if we grind the cutting insert normally, then the RZ is better than 1. And this makes sometimes problems, especially for sealing diameters, because the oil does then not adhere to the surface of the workpiece, and then the seal is no longer lubricated, and so it gets thermal damage. And so the possibility to make this better is that we make the surface from the part rougher, so that the oil can glue on the surface, and the sealing doesn't get a thermal damage. Because of this, we have the two different inserts. On the left side, the insert for a sealing diameter with RZ 1 to 4. Twist pitch is 0. This means that it's lead-free. then the RZ is normally between RZ 2.6 and 2.9. This is why it's a bit different than with a conventional turning. If we start with RZ3, over the tool life, the surface quality gets better. So normally we start at the upper side of the tolerance, and then it gets a bit better during the tool life. Our max is normally between 0.95 and 3.2, and the depth of twist between 0.45 and 0.8. The extracting area is less than 60 microns. And then let's have a look at the other cutting insert. It's the cutting insert for the best surface quality. It's also possible to produce a lead-free surface. RZ is normally between 0.5 and 0.9. Our max between 1.2 and 1.6, and depth of twists between 0.1 and 0.35. The extraction area is normally less than 20 square microns. So, what are the advantages of the skiving process compared to the conventional turning? We have a greater process reliability because the chips, if we have a look at the hard process, the chips are absolutely no problem because they get very hot, and so they burn up and get brittle, and so we have no problems with the chips. If we have a look at the soft machining process or soft skiving process, then you always have continuous chips. But as the continuous chips are no problem here because we can control the flow of the chips that they don't touch the workpiece or the insert after the machining. Then we can reduce the non-productive time. Why? Because of the higher tool life. We have fewer tool chains, and so we can reduce the non-productive time. And why we have the longer tool life, I already told you, because every point of the insert has only a very short contact to the workpiece. All things, how we can reduce cycle times is the high feed rate and the high cutting speed. The high feed rate, we can produce very good surfaces with a high feed rate because of the 45 degrees and the long cutting insert. The cutting insert smooths the surface at the end, and so we can machine with very high feed rates. And the high cutting speed is because of the short contact point, and that because of every point of the insert gets a small thermal influence. So we come to the next point, applications and examples for the skiving process, and for this my colleague Andreas Truffe will tell you more about.
Yeah, but first we have the next question.
Okay.
Can scroll-free turning also be used for interrupted cuts?
Yes, interrupted cuts are absolutely no problem. You have a bit less tool life, but normally they are no problem, because if you have a look at the standard turning process, you have always a hit. If you have an interrupted cut, the workpiece always hits on the insert. And because of the 45 degrees, if it comes to then, you have a very smooth, the entry and the exit of the insert into the workpiece is smoother than with the standard turning process.
Okay, thank you. Okay, now we come to some application examples. As we have seen, the skiving process is mostly required for good surface quality, maybe for scroll-free seats for sealing rings. And these requirements you find mostly on shaft machines or shaft workpieces. And for this reason, the following examples are taken from shaft machining. But also the following examples, you will see it makes sense in some cases to use the skiving process also for flange parts. First example is a comparison of tool change time, and we have to do some assumptions for it. We have a bearing seat, it's hard turning. We have a diameter of 40 millimeters. We have a length of 30 millimeters, and we calculate it with 2 minutes for a tool change. And now you see for conventional hard turning, with a tool life of 20 minutes for one cutting edge, you can do 150 work pieces with one edge at conventional turning, and in comparison, the skiving tool would have a tool life of 3,000 work pieces. This is a very conservative assumption. And with this calculation, you can see to get it more easy, we calculate for the 3,000 work pieces what we can do with a skiving insert, and for this you would need 20 tool changes for a conventional insert. And if you look for the time what you can save, this would be 38 minutes for these 3,000 work pieces, or approx 1.3 seconds for one workpiece. Next is the comparison of cycle time. First example, we have a hard turning process. We have conventional turning with a cutting edge radius 0.8 millimeters, and we need a surface with RZ smaller 4 microns. And depending on lengths and diameters and the surface, the skiving process can also reduce the cycle time. So in the calculation, you see the finish turning with a conventional cutting edge. We have a surface speed of 160 meters. And for the surface, we need a feed weight of 0.11 millimeters. This would need 12.9 seconds. And after it, you see pre-turning with a conventional insert, same speed, but higher feed weight, because we don't have to look for the surface in this moment. This needs 5.7 seconds and additional 4.5 seconds for the skiving process with a speed of 250 meters and a feed weight of 0.2. And in comparison, we are 2.7 seconds faster with the skiving process. And that's it for the hard turning. We have to do the pre-turning because of the run-out and the quality of the raw part in the machine, and we need a very good run-out and good quality in clamping situation. And because of this, we do the pre-turning for the skiving process. Next would be an example for soft skiving. Here it is a rotor package. Conventional turning would be with a cutting edge radius 0.8 millimeters, and we need RZ16 for the surface. Because we also have to do the pre-turning in both cases, the advantage of the skiving process is higher. And here you see finish cut with conventional inserts with 280 meters surface speed and feed weight of 0.24 millimeters with 22.7 seconds. And the skiving process surface speed is a little bit lower with 250 meters, but the feed weight was 1 millimeter, and so we need 6.1 seconds, or we are 16 seconds faster than with a conventional cut. Now we have an example. Here you see a shaft of a rotor shaft, and we turning with 250 meters with a feed weight of 0.3 millimeters, and we have a cutting depth of 0.15 millimeters. First we do the pre-turning for the skiving diameters hard, and with skiving we get a surface of 1 to 4 microns. You see the skiving, the first diameter, skiving second diameter, and then we do skiving soft in the middle area with RZ4. Roundness will be 5 microns, and the cylindrical shape at around about 8 microns. Now we see a rotor package. We have seen similar shaft before, and now we have to look for the rotor package. It's always a laminated core, and we have to do to avoid the bars between the laminations. And in this example, we do the soft skiving of the rotor package, also 250 meters with a feed weight of 1 millimeter. It's the same what we've seen before in the cycle time calculation, and the surface with RZ 6.3 microns. This is a VT200 machine for shaft turning with 4 axes. We do the pre-turning with round inserts. And after it, we do the skiving process with a white turret. And you see we have a nice surface, and it's very fast. Okay, I have the next question. Two life specifications were between 3,000 and 10,000 parts. What does it depend on? Daniel?
Yes, there are a lot of reasons for the different tool life. One thing is, of course, the material of the workpiece. This has a big influence, and another thing is the clamping of the part. The clamping must be stable for a skiving process because of the higher higher forces. And sometimes if you have not a perfect clamping or a very small part and so on, sometimes we have to change the preparation of the cutting inserts. We have to make it a bit sharper, and this reduces the cycle time, the tool life. And what's another reason? Material, clamping, and the preparation of the cutting insert are the biggest influences.
Okay, thank you. So, have a look on the machines, what we use for the skiving process. We have seen mostly required in shaft machines, so we have the VT2 or VT4, 2 different sizes of the shaft machine. And VT2 or 4 is equipped with a Fano control unit. But we have also the VT100 or 200. It's the same machine, but with Siemens control unit. And on the right side, you see the VL series. We use this machine for flange parts, and the VL3, VL8, so different sizes of this machine. Because we have most of the time skiving in the shaft machines, you will see here the working area of VT4. You see left and right turret and a gripper on each turret for simultaneously loading and unloading the parts through the machine from the left to the right or from the right to the left. And this guarantees us to have very short loading and unloading times. And on the left and right turret you see the skiving tools in the start position for work. So we have a conclusion, and what we have seen, we have the fastest turning operation with high surface requirements. We have low invest, especially compared with the grinding process. We can reduce the process costs, maybe with tool change, dry machine, cycle time, and so on. We have a more environmentally friendly, thanks to dry machining and low energy consumption. We can do scroll-free turning, scroll-free surfaces. We can do hard and soft machining, and we have a high flexibility compared with a grinding machine. And now I have the next questions. First is, can I retrofit scroll-free turning with any machine? I say yes, if you have a good clamping situation, and if you have a y-axis, in principle you can use each machine, but I think you can imagine we highly recommend to use the EMAG machine. And second question, can flat surfaces and contours also be skived? I think Daniel will give you the answer.
Yeah, I think flat surfaces are not possible to produce with a skiving process. You can do something which looks like a skiving process, but that you have the moving contact point over the cutting edge is not possible. You only cut with one edge, and you don't have the effect from the skiving process. Contours are possible, but it depends on the contour. If they are too strongly curved, sometimes you get collision between cutting insert and the workpiece. Yes, if they are not so slightly, if they are only slightly curved, then it's possible. Yes, a cone is also possible.
Okay, thank you. We have the next question. What is the smallest machine where a skiving application is available? I guess the machine size doesn't influence the skiving process. We could use it with a VL3, I think, up to what you want.
I think every machine which has a y-axis we can use for the power for the skiving process.
Yeah,
that's possible.
Okay. So at last, you will get an email with my contact address if you have any questions later, and don't hesitate to send me your questions, and I will try to answer it as fast as possible. And you have also the possibility to see this webinar or the presentation later in our EMAG homepage, and there in the Mediathek you will find this webinar and the presentation. And now I wish you a nice day, and thanks a lot.
Bye.